Hey everybody, and welcome back to Linear Algebra Online. So the plan for class today is really to see a pattern with the eigenvalues of a matrix to a power. So there's some sort of connection, like if you have like a matrix A and like eigenvalue lambda, let's say, there's going to be something interesting that happens for a to the n, and like what happens to the eigenvalue for that matrix. And the thing that I'm going to have you work through kind of gets you there without just flat out telling you it, and it's a very useful result. And just really quick, kind of unrelated to that, honestly, just I wanted to do this problem. So last time we saw the computation of the eigenvalues for a triangular matrix. I think we had one that was like maybe a 5x5 matrix or so. And we talked about how the eigenvalues would appear on the diagonal. And I think it's good to just kind of see the structure of a proof for something like that. So to kind of start off, what I would do here is you could just say something like, note a minus lambda I is also triangular, right? I guess you could even just add a little bit, since I is only non-zero on the diagonal. Right, so when you subtract those two matrices, you're only affecting the diagonal. You're not introducing a term in the other parts of the matrix, thus like messing up the triangular structure of it. So that means that like if, basically the only entries that are changing are like the I kind of entries. So I'm just going to say the only entries changed between A and A minus lambda I are ones of the form I minus lambda, right? So this is just like an arbitrary row and arbitrary column, basically. So the ones on the diagonal, right? And then we know that, the determinant of a matrix like that, A minus lambda I, then, for any triangular matrix, right, we know that the determinant of it is just like the product of those diagonals, like A11 minus lambda times A22 minus lambda times all the way up to like A and N minus lambda, right? And so we see basically lambda 1 equals like A11, lambda 2 equals A22, lambda n equals A and N. And, we know that just since we set the determinant equal to 0 to find the eigenvalues. And that's basically it. So it's just kind of a more formal version of how we would break down why the diagonal is really the eigenvalues for a triangular matrix. But the main plan for today is really not related to that. It's related to this thing. And there's going to be an assignment that I'm going to have you look at that's going to kind of walk you through the important thing that's happening for A to the N and what's happening with the eigenvalues.